All right, welcome to our fourth lesson for chapter 9. Chapter 9 is all about non-renewable energy. Most of the time when we're talking about non-renewable energies, we are talking about fossil fuels, which is what we've been covering up until this point. In this lesson, we're going to talk about nuclear power. So nuclear power is a non-renewable energy, and we'll talk about why, but it is not a fossil fuel. So learning goal or learning objective is that you'll be able to explain the conceived risks of nuclear power and the different types of radiation. So although nuclear power does not come from a fossil fuel, it is fueled by uranium, which is obtained from mining and is non-renewable. So because it's from mining this element, this radioactive element, it is non-renewable. Uranium isn't, there's not more uranium being formed in any time period where, it's forming and then we're able to mine more. Once we mine it, it's gone. As of September 2020, there are 441 nuclear power reactors in operation, and there's 53 nuclear power plants under construction in 19 countries. Of the 106 that are currently being planned, most are in China, India, and Russia. This is what a nuclear power plant looks like. It looks kind of scary that it looks like smoke is coming out of these towers. This is just water vapor. So these are cooling towers. Nothing is really happening in these towers. We'll look at what those look like on the inside. Most of the things are happening like in the actual reactors. These are the cooling towers where it's just cooling off the water. So there are people who love nuclear power. There are people who despise nuclear power. And there's a few things that influence those attitudes. So the number one is concerns about safety. So there have been 3 really big and significant nuclear power disasters that kind of, bring up concerns with safety. But those could be with accidents. There's also concerns with safety and decommissioning. That's when we shut down a power plant. And then also with terrorism. The other concern is climate change. So even though nuclear power is a non-renewable energy, it's a very clean non-renewable energy when we talk about climate change because it does not release carbon dioxide. There's also just in general anti-nuclear attitudes. We think about nuclear weapons and then nuclear power and relate the two. And while they are related, they are different. And then the economics of it. So building power plants is expensive. So building power plants is expensive, although they do burn, or they are a cleaner form of energy, but it is cheaper to just use fossil fuels, which we use already. So I'm not going to go over this whole thing, but you can see where there are reactors or what countries have a lot of reactors. So across the world, 441. The US has 95, even though nuclear power is a very small percentage of our power, 95 because we are a pretty big country. France is 56. France gets actually most of their power from nuclear, but they're much smaller than us. So if we look at the US, this is where all of those power plants are, mostly on the eastern side of the country, a few on the western side. So to understand nuclear energy, we need to talk a little bit about some chemistry things. So the nuclei of certain atoms. So in atoms, the nuclei is the center of the atom where we have our protons and our neutrons. So the nuclei of certain atoms are unstable and spontaneously decompose. So if they were stable, they would just stay the same. These are unstable, so they just kind of break apart. Those are radioactive. So the neutrons, electrons, and protons and other larger particles are released during nuclear disintegration, along with a great deal of energy. So anytime an atom is going to break down, it's going to release energy. The radioactive half-life is the time it takes for half of that radioactive material to spontaneously decompose. And if we look at the different radioactive isotopes, we look at the half-life of how long it takes them to do it naturally. So like radon is pretty quick. Uranium, which is what we use in fuel as power plants, takes 700 million years. So while it is radioactive, it is a little bit more stable than some others. With radioactive decay or nuclear disintegration, those releases of energy from the nucleus is known as radiation. And there's 3 different types. The first is alpha radiation. It looks like this fancy A. And that consists of moving particles composed of 2 neutrons and 2 protons. So it's just part of a nucleus, no electrons around. And alpha radiation is fairly safe. It can be stopped by the outer layer of skin. So if someone was, throwing some alpha radiation at you, your skin's going to stop it. The next is beta radiation, which consists of the electron. So remember, our nucleus our atom has started to disintegrate. So we have parts of our nucleus, that's going to be the alpha radiation, and then the electrons is going to be the beta radiation. It can be stopped by a layer of clothing, glass, or aluminum. So if you are wearing like full body gear, you're protected, but if you have skin out, not protected from beta radiation. Last and certainly not least is gamma radiation, and that's a form of electromagnetic radiation. So not really a specific particle, it's just like the energy basically coming off of it. And that can pass through your body several centimeters of lead or a meter of concrete. So dangerous, a lot more dangerous. All right, so when we actually have this nuclear chain reaction, we have the radioactive isotope that wants to break down. So nuclear fission occurs when the moving neutrons impact and split the nuclei of other atoms. So we have our nuclei that are breaking down, and it's shooting off the particles. One particle will hit another atom, and then it breaks apart, which we'll see on the next slide. And that causes a nuclear chain reaction, where they're all kind of striking each other as these reactions are happening. So it looks like this. So this is a neutron that has shot off from another uranium atom that has broken down. That's going to hit another atom that then causes that to break down, which is going to hit another atom, which causes that to break down. And each time they get hit, a neutron comes off as well as some energy. And that energy is then harnessed to create electricity. Only certain kinds of atoms are suitable for the development of a nuclear chain reaction, and the two most common are uranium and plutonium. Uranium is what we use in nuclear reactors for power plants, and plutonium is more frequently used for nuclear weapons. And there's also must be certain quantity of nuclear fuel for the chain reaction to occur. So if we have just like a handful of atoms, they're not really close together, it's less likely that that neutron, when it pops off, is going to run into another one. So we need enough of those atoms all together for this chain reaction to occur. So we're going to look at a nuclear reactor, and I'll point out all of the little parts. But a nuclear reactor is a device that permits a sustained, controlled nuclear fission chain reaction. And the most common nuclear fuel, again, is uranium-235, or U-235. So when the nucleus of uranium-235 atom is struck by a slowly moving neutron from another, the nucleus splits into smaller particles. That's what we saw in that picture. More neutrons are released, which then strike more atoms. And the chain reaction continues to release energy until the fuel is spent or neutrons are prevented from striking the nuclei. And this is what a reactor looks like. So again, these are those big cooling towers we saw. Cooling towers are literally just for cooling down water. That is it. Nothing else is happening over here. If we look at nuclear power plants, there's usually like a dome-like structure where the reaction is actually happening. So what's happening is in the reactor, this is where those reactions are happening, this like red box. Control rods, they can control those reactions happening. So the control rods will raise or lower to kind of control how quickly they are happening. If the control rods weren't there, it could happen too quickly, and that's when we have accidents. So the reactions are happening here. This is water, this purple right here. This water just cycles through. It's a closed, in most nuclear reactors, it's a closed system. So these reactions are happening. It's releasing energy. That is causing this water to get very, very hot, to like beyond boiling. But it's a closed system, so it's just pumping through. This hot water then leaves that reactor and is piped through another container of water. Then water's not mixing, they're just like the pipe is so hot that it is then causing the water in this area to generate steam. That steam then comes over here, turns a turbine, which generates electricity, which is then distributed. The water from the steam condenses back into water and then goes through the system all over again. and the water being piped through the cooling towers comes and helps cool that water down. So it comes out so hot, that's the steam that's coming out of the cooling towers. All right. I know that was a lot of information in one. If you have any questions, please let me know, and I will see you